to bar magnets. Main purpose to measure the distance dependence of the magnetic field due to a bar magnet, and use this to find the magnetic dipole moment of the field, and then compare our experimental results to the predicted results of BNet for an off-axis field using derivations of Biot-Savart law and a computational model. Main results, I got n is equal to negative 2.9599, mu is equal to 3.985 amp meter squared. Experimental magnitude of the magnetic field was 7.024 times 10 to the negative 5 teslas, and the computational magnitude of the magnetic field was 5.8304 times 10 to the negative 5 teslas. So some key physical principles. We have the distance dependence formula, which states that the magnitude of the magnetic field of a bar magnet is equal to k times r to the n power. And the reason why this is important is because the magnetic field due to a bar magnet changes with distance. And then we also need to know that the magnetic field of a dipole off axis is equal to this nifty little formula right here, which was used to show visually the, and I guess calculate the magnetic fields using the computational model. And then we also need to understand the Biot-Savart law, which describes the magnetic field generated by a constant current. So initial conditions and assumptions, we're assuming the bar magnet acts as a magnetic dipole, and we're also assuming the magnetic field is perfect, sorry. Some initial conditions for finding the off-axis field was that the magnetic field had an x component of 20 microteslas, and then we kind of changed from there. But also our phone was oriented to compensate for Earth's magnetic field, which for me was a reading on the magnetometer of about 48.4 microteslas. The system is the bar magnet, and the surroundings is literally everything else. So experimental procedure, basically we found the magnetometer chip on the phone and then used this as a reference point to measure the distance between that and the bar magnet for both the on and off axis values. And then for the on axis, we had to record the distance at r equals 20, 70, 120, 170, and 220, and we repeated it twice for a total of 3 experimental values. And then for off axis, we measured the distance so that the net magnitude was 100 microteslas, recorded the y component, set up a 45-degree triangle, and recorded the measurements. So some data analysis. These are just my numbers here for the on-axis experiments. And then here we have, the most important thing here is that ln bx, or y in this case, is negative 2.9599 x minus 14.043, which I used in a later calculation. And then here's also my off-axis field values. So I got my average dperp to be 0.156 meters. And you can see here that my BNet was 7.024 times 10 to the negative 5 teslas. So for my calculations here, like I said, ln bx is equal to this equation here, where x is equal to ln r. And then for the negative 14.043, that is equal to ln k, where I substituted that in here and got that k is equal to 7.97 times 10 to the negative 7. And then I just plugged that into the distance dependence formula, which gave me the magnitude of b bar, and we know that we're treating the bar magnet as a dipole, so the magnitude of b dipole should be equal to the magnitude of b bar, and then just using Biot-Savart law, substitute in, find mu, and I got 3.985 amp meter squared. So the computational model took the observation locations of all of both the on-axis and the 4 off-axis values, and then plugged that in, and this was my visual model that I got. So discrepancies between, also this is where I got the magnitude of 5.083 times 10 to the negative 5 teslas. So discrepancies, the computational model is more likely to be accurate, as my experimental calculations are more prone to human error, obviously. And the reason for this would be that other electronics may have affected the reading of the magnetometer. I have an Apple Watch. I didn't have it in the room with me, but it was in the other room, so I don't know what the radius of effect would be. There was a laptop in the same room as me. Also errors with the magnetometer app, mostly user error. I kind of just had a problem with like keeping it steady and having like a steady reading. It was kind of flip-flopping all over the place, and also I had to keep closing and reopening the app, so I may have shifted my phone a little bit to misalign it. And then also some observations were that when the magnetometer is far away from the magnet, the magnetic field is close to 0 in the x direction, and as we move it closer to the bar magnet, the x component increases. So for the what if we didn't compensate for the Earth's magnetic field, then it would skew the reading on the magnetometer, which would alter every further calculations. I think that it would have resulted in a higher magnitude of the magnetic field. I'm not entirely sure, like, what degree, but I assume that it probably matters a lot since we compensated in the first place. And then if we were to stick two identical magnets together and run it again, then every value would roughly double, as the magnetic field would double in strength if we added another magnet to the system. Thank you.